So please make sure you get enough reading done if you are into research line and stuff. Okay, let's now go into part 2 of resilient behavior or repeated loading behavior, which is permanent deformation. We talked about resilient modulus. Resilient modulus is an important input for your MEPDG, mechanistic empirical design and stuff. Repeated loading behavior, it's more performance, right? It's not an input. We don't need a model input to run this or anything, but it is a very, very important component because it actually governs your rutting behavior and stuff, right? And rutting is a major distress that you have to address and whatnot. So it is an indicator of how much loading or what level of stress the material can exert, and then how does that affect the fabric of it. It's not really fatigue, but you can actually think of it similar to fatigue, because even if you are not near failure stresses or something, but if you just have many load applications, at one point the fabric of the aggregate matrix or the unbound matrix actually can collapse, and you can actually have, look at this curve, you have load repetitions on the x-axis, permanent deformation, and actually stayed. After some time it just collapsed. There are many factors that affect it. One is, where do you stand with respect to the failure stress of the material, shear strength, right? The way I explain it is, let's just say you are into weightlifting, okay, and your capacity is, I don't know, 100 kgs, right? To lift, you can probably do 50 repetitions, like not near my capacity or anything at all. But if you are lifting 8 kgs, then even after say 20 repetitions, you'll probably get very tired, right? So the nearer to the failure stress you are, the lower the number of repetitions before you actually start collapsing and stuff. That's basically what it can be translated into shakedown theory. I know some of you are studying shakedown theory and stuff. We'll talk about that a little bit. But how do you represent a model? We'll take a look at that, and how do you study it. So as I said, general resilient modulus testing. Okay, I think let's just get there. There is no standardized permanent deformation testing protocol. Okay, there is no ASTO T309 or something that is resilient permanent deformation. There is no. There have been proposed methods, there are suggested methods, but it's not standardized. There are many reasons for it. But in the resilient modulus testing, I said the sequence 0, not in the data. In the data, sequence 0 meant something else, but I'm talking about when you define the test procedure. I said it's a 15 sequence test, but before you start it, you do what is known as the conditioning, right? And the conditioning represents the material, initial breakdown or initial stabilization of the material. You can use that data as an indicator of the permanent deformation trend of the material. Okay, how many cycles do you run that for? I said 500 to 10,000 or something like that, right? Usually it's about 1,000. Like all the tests I have run, it was all 1,000 cycles, so it's about 16 minutes. 16 minutes is what, 960 seconds. So 40 more, 16 minutes, 40 seconds basically. So the point is, that's what this plot is saying. The general MR test procedure, if n equal to 1,000 or up to 10,000, or at least 10 or at least 3 log cycles, You know what a log cycle is, right? A 0 to 1, 1 to 10, 10 to 100, 100 to 1000. That's a log cycle. So 1 to 10 is one cycle, 10 to 100 another cycle, 1000 is another cycle. So at least 3 log cycles. If you run it, you will get some idea about the permanent deformation trends. Now, permanent deformation is not a very easy thing to capture immediately, because it is dependent on several things. If your material property, because it's a long-term phenomenon, right? If your material property changes, what does that mean? It's raining and your layers are completely flooded. Your material is not the exact same material as it was. So now your shear strength, so you're now lifting still 50 kgs, but you're lifting 50 kgs after partying for all night and not getting enough sleep or not getting water or anything. So your capacity has gone down. So it's not a factor of 2. It's not that your 100 kgs your capacity has probably gone down to 75. So the same load, if your material property has changed, is going to collapse your system now, right? Other way around is if the loading magnitude, right, whatever is designed for, somehow the loads are getting heavier, right? We actually run into this problem, if I am not wrong, in a lot of rural roads in India as well and stuff like that. Probably they didn't think about it. They just thought maybe a bus or something will go, and all of a sudden a tractor with a lot of bricks and stuff, like completely fully tractor runs on it and the pavement just falls apart, right? That's what is your design vehicle and stuff like that. So this is, you can actually get an idea. Construction and initial shakedown is where you have this exponential raise, and then it kind of stabilizes. A permanent deformation behavior should always be like this. It should always stabilize. Because remember what's happening here. Who can tell me when we are loading here what's happening? This is the hysteretic part, right? We talked about in the resilient modulus. That's the flat portion. So ideally you should be operating here. But that always stay flat? No, it can change because of many factors. The very standard model that gets fitted into permanent deformation, the most commonly used model or to talk about, is what is known as a phenomenological model. Okay, is of the formulation an to the power b. A and b are constants. N is number of load repetitions. Okay, at first glance, what is missing from this model? Well, we'll get to that. Modulus is an elastic parameter, right? We don't need that here. Let's just say material is constant, let's just say climate is constant. Yes, they're all true. I mean, you're all right. But for a given material, even, you cannot anyway consider climatic or material properties. But what is missing here is stress. You're not saying what is the stress level under which this test is being run or anything. It's just an an to the power. N is just number of load. How many people are there? Like, it doesn't matter. It doesn't really say anything. Go into the details of this model. Why it has worked over the years is because this A parameter actually is a function of stress state. You are not capturing directly the stress in the equation, but A actually captures indirectly the stress effects and stuff. And B is less sensitive to sigma, and it varies with soil type. So A factor, or different things like soil type, moisture, density, strength, and stress level. This is something we are going to hit pretty hard, most likely after the tea break today. Is the concept of what is There are two ways to talk about it. First, sometimes people call it as subgrade stress ratio as well, SSR. It's the same SSR. It can have two different meanings. We'll talk about this extensively after the tea break. The whole idea here is sigma D over QU. What is QU? Unconfined compressive strength, right? And then sigma D is deviator. How much are you demanding of the material with respect to ultimate value, the unconfined strength? That's called something called subgrade stress ratio. It actually affects your resilient modulus, permanent deformation significantly. We'll take a look at that. And in this, again, remember folks, why I said model fitting is very easy. Look, log epsilon p is a plus b log n. Does that look familiar? We just did it, right? Kn, k theta to the power n, right? We did the exact same thing. Oh, yeah, why did they do log a? It's probably log a, because a is a constant. They actually say log a is another constant, basically. You're right. It's not exact, but it's basically a is a. It's a constant. So it should have been ideally a prime or something, right? Log a is a prime. Kuch alag naam. Yes, you are right. Absolutely right. But the whole idea, we have done this, right? K theta to the power n. So if I give you epsilon p data, and if I give you n, you should be able to fit this model very quickly. We just did this, right? A factors for granular materials, it's shear strength and the ratio of sigma 1 over sigma 3. Again, there is nothing called QU, remember, for granular. It. Now you're talking about holding it, how much we are torturing it, sigma 3. That's ratio. So this is what's affecting your permanent deformation. Permanent deformation testing is much less advanced than resilient behavior. It's not standardized. You don't have a standard protocol, but you have to, if you are studying the rutting behavior of a material, different people have different test protocols, different stress states. How are you going to test it and stuff? There's a lot of decisions that makes into subgrade and unbound batch material performances solely judged by their field performance deformation or rutting mutation. So it's basically saying that I will make health condition by measuring or by looking at how your blood sugar is or something, but I don't give anybody a method to monitor their blood sugar or something, right? So that's essentially what you're talking about. So we don't have a standardized test method, but every time we do payment performance prediction, we track rutting and we say, oh, it's bad. But we need to test it then. Not fair. How do you test it? Again, no standardization. It's repeated loading. That much we know. It is still Haber sign. That much we know. We have rest period and stuff. That's much we know. But number of load cycles can go from 1,000 to 8 million is what people have seen. So 8 million is 8,000, right? So can somebody do 8,000, 8,000 divided by what? How many seconds in a day? 86,400 or something, right? Is it 86,400 or 84,600? 86,400. Can you do that? 8 million divided by 86,400. I just want to see how many days a test takes. 92. So it takes 3 months, right? Now imagine your advisor asks you to run 50 of these tests, then you are like lifelong PhD student or something, right? You never graduate. So it's very difficult to track, these long tests and stuff. How do you do loading? It's more common is CCP. There is actually a VCP procedure in Europe available as well. As I said, for stress states, for cohesive soils, you decide on something called subgrade stress ratio, SSR. Okay, and there are some rules of thumb, and I may not have a slide on this, but I'll tell you this. If you are, let's just say you are helping an undergraduate student do a little design of for a project or something, and they're like, hey, I'm going to put 5 inches of an asphalt, 12 inches of an aggregate and stuff. Is my subgrade going to be okay? You're going to say, okay, what do you have? Like, I don't have anything. I have only CBR. Like, okay, that's a good starting point. We don't have anything and we still have to have a result. Let's do a CBR to unconfined compressive strength correlation. That's still okay because both are strength related. So you're still doing okay. So you determine QU and then you run a simple IIT PAVE or something to determine the deviator stress on top of the subgrade. And then you take the ratio. The rule of thumb is that as long as it is less than 0.6, fine. It's a rule. Don't ask me where. It's very empirical in nature. Of course, 1 means what? Say it again. Both are same. What does that mean? What will happen to your subgrade? It's going to fail, right? You're going to collapse. So sigma d over u, the rule of thumb they say in very elementary design is limited to below 0.6, 0.7. You should be fine. You will not have rutting problems and stuff. So you can, and coarse aggregates, you can have sigma d over sigma 3 or sigma 1 over sigma 3, however you want to do, and then you can monitor the delta p and stuff. What are the primary factors that affect permanent deformation? You can have applied stress states, you can have QU or tau max. Again, we're going to look at tau concept very in details after the lunch break, after the tea break. And then you take that. And the secondary factors, you can have moisture content, plasticity index, clay content, dry density, freeze thaw effects. Okay. Now freeze thaw is something, I don't know, maybe in northern India it's considered like really north, maybe I'm assuming, but other parts no, you don't really freeze. But freeze thaw is a major problem because freezing is a very good thing, right? Because ice is very strong, your soil becomes really strong. The problem happens when it's thawed. Now it becomes like a mush, right? And also just you can do this test. If you take like a little soil cylinder and you put it in your freezer and then you take it out, put it outside, put it in the freezer, take it outside, you'll see that the soil fabric actually disintegrates even if you don't do anything about it. The pore volumes and the pore structure and everything collapses and stuff. So freeze thaw is a very big thing. So let's take a look at some of these. This block or this section is very data based. You'll see I have a lot of test results to showcase some of these things. So you have seen this. This is basically increased sigma increases epsilon b. These are two different materials: medium subgrade, soft subgrade. Medium subgrade unconfined compressive strength of 23 and soft is 13. Two different subgrades. Okay. Sigma d, b and a, and look, the b's as the sigma d, so it's basically 0.14 to 0.17 for different stress states. So the b is not very sensitive to stress in the model a to the power b. Okay. The a on the other hand can be very sensitive depending on the material, on the stress combination. For the good material, relatively good, initially it was just subsensitive and then it became very sensitive at the higher stress states. For the soft material, throughout it became very sensitive, right? So let me show you what does that represent. So if you look at a n to the power b, right? Epsilon p is equal to a n to the power b. If you take log log A plus B log n. What is log 1? 0. So A basically represents the put n equal to 1. 1 raised to the power B is, so epsilon P is, so A is this initial hammering that the material takes, right? That's the intercept, right? So what you are seeing here is as the material gets soft, even for a little stress increase here, it's taking a big hammering. Does that make sense? So that's what I want to highlight, is that is not necessarily, man, I broke another one. I'm on a roll. They're going to charge me money now. What I'm trying to say is, depending on the material and the stress state combination, it can be very different. The effect. This one. This is sigma level, sigma D. Okay. Sigma D is 15, 30, 50, and then this is 60. Okay. Look, 15 to 50, you did see a little bit of increase in strain, but not something that you should be worried about, or not something you should be panicking about. But look at what happens when you 60. So that's what the boundary is. You are going to go high with respect to the subgrade stress ratio that your material just going to collapse. Remember, resilient modulus is a characterization test where we are intentionally applying stress states that are very, very low compared to shear. Rutting or permanent deformation is something where you are measuring, you're trying to challenge the material to say how not keeping it very low or something. We are pushing it, right? We are saying, where are you going to collapse? That's my rutting behavior, right? This again is the same thing. QU, remember I said 50 to 60%, 60, 70% you can be high. In this data, it's about 50% of QU, you are fine. You go to 75%, you go to 100% and stuff, collapse. How repeated loading you're applying and stuff, right? So the whole idea is, it's a pavement. Remember what I said at the very, I think day 2 maybe, or day 1. I said when you track critical pavement response parameter, you all gave me vertical strain at the top of the subgrade, and I say I personally believe in vertical stress more than strain, and we'll see a little bit more in a few slides. But this is the reason, because the stress directly compares to strength. Cutting is governed by strength. Cutting is, so now the question is, what would you rather correlate CBR with? I would rather correlate CBR with shear strength, which would give me an idea of the resilient modulus, because modulus is not teaching kind of a behavior. Modulus is not a torture test. Modulus is not something we're trying to get. That makes sense? So this is a clay material. There is a clay versus silt. The clay has a higher unconfined compressive strength, and how the behavior changes again, 75 to 100, it just collapses. Another data set, I'm just going to skip this one. This one is again SSR, the same stuff, subgrade stress ratio. 1 means it's equal. Look what happens. Collapses with load application. Only less than 60, 70 load applications, it's gone. Material collapses because you are demanding way too much of it. You stay lower 0.25, 0.5, 0.75. We're okay. We're still 7.5. The the reason we advise not to go to beyond 7.5 is it's only 1,000 cycles. If you look at make it 10,000, you'll see actually it probably goes very high or even collapses at the point. Here you're in really safe range. So designs and stuff, any material being tested, the stress is low. That's the whole concept of protecting the weakest layer, right? Rutting is a good representation of protecting the weakest layer, right? This is, you already saw this. This is sigma d over qu, less than or equal to 0.5, 0.6. This is what I said. You keep it in that range, you'll be fine. And this is C is the cohesive. There's nothing new here. This is an effect of moisture. Now we are talking about the same material, but now the person slept at night before or was partying drunk the night before, right? So 30%, the same material. We are still maintaining subgrade stress ratios and stuff. Look, at 0.25, it's not a big problem. 0.5, it's not a big problem. 0.75, now the material is so much weak that the 0.7, it's actually starting to collapse now, right? Moisture effect is very bad. Effect of W, again, moisture content. This is optimum. This is optimum plus 3%. This is optimum plus 4%, right? So where do you compact your material? Again, we don't in this course, but you know that in the bell-shaped, same density at 2 water contents. Where do you compact? The dry side or on the wet side? Well, depending on what compaction theory you are going. If you go by the lubrication theory, right, then you're not talking about flocculation versus dispersion and stuff. You're just talking about strength. It's more things, right? It's stronger. Can you think of one example or one case? And you all should do this. Actually want to compact on the wet side? Say again? Why? To reduce the permeability is yes, one reason. Let's talk pavements. Yes, on the wet side you have reduced permeability because you have more water. Pavements, when do you compact on the wet side? When you have a material that is very sensitive to expansion and stuff with higher water contents like expansive soils and stuff, it is not uncommon to actually almost flood it or compact it on the wet side. Make it expand as much as it wants. Take care of all the expansion and then somehow with a geomembrane or something prevent further moisture changes and stuff and build on top of that. You don't really want situation to be happening. It's very limited cases, but yes, permeability can also be another case. Okay, this is again moisture content. You know, at lower moisture content, it is 23 is good, but beyond at one point, it like 26, 28.5, 30.5, it was kind of similar and stuff. This is freeze-thaw cycle. Okay, another very important thing that you should pay attention to. Freeze-thaw cycle collapses the internal void structure of a clay, of a soil, and it actually becomes very susceptible to failure and permanent deformation. So the same material, okay, no freeze-thaw cycles. Look at the rutting. One freeze-thaw cycle. No, what? Yeah. Sorry. Yeah. 15 is the sigma d. 15 is the sigma d with no freeze-thaw cycle, and 30 is the sigma d with no freeze-thaw cycle. So this is not free, those not exposed to freeze thaw from 15 to 30. Look at how much increase you have. Here, one freeze thaw cycle 15 to 30. Look what that would do. Same soil, same material. Just one freeze thaw cycle collapses the void structure completely and the soil matrix, and you just become much more susceptible to. Uh, how much does water expand when it freezes? Come on. 9%. It's a trivia I asked all the time in my class. I thought you guys will know this. Okay. Subgrade soil. Okay. Now, let's break now. This is a good breaking point. We have 3 minutes, or we can have 3 minutes of discussion. But because this is a very important concept of using resilient strain to predict permanent deformation. Remember, that's what we were talking about, like strain on the top of subgrade, and why I said no. It's going to take some time. So it's a good natural breaking point. But we have 3 more minutes. So if you want to, any questions, address during that time. It's not 0.06, 0.6, 60%. Don't apply more. Can you? Here? There is a point here. That's 1.00. So this is equal, and then this is 50%. 60% is somewhere here. So for repeated loading and stuff, 6, if you have a low volume road, go a little bit up 0.7, not more than that for sure. 0.65, not more than that. Any more? Anything else? Yes. Well, if it's an unbound material and if it shows stress dependent behavior, maybe yes. Now wrap has some funny properties sometimes. Like wrap, uh, it's very interesting sometimes. If you sure, if you do resilient modulus testing, wrap will give very good numbers. But if you do rutting testing, wrap will actually give bad numbers because the asphalt kind of lets it collapse a little bit more and stuff. So how is it captured? You'll just have to study. I mean, I don't think there is any theoretical answer to your question. Yes, for everything morphological properties affect, right? That's what the angularity index, the surface texture index and everything, that's what it was. So yes, if your material changes, like for example, slag 1 versus slag 2 or aggregate versus slag, so now you are not just changing the material, you're also changing the angularity, you're also changing the surface texture and stuff. So you have to have some way of normalizing it or trying to balance it out. The models consider the role of stress history. In the resilient modulus test, no, right? It's under the given sequence and stuff. And stress history, yes, it's very important. But in the resilient modulus, we are talking about just initial shakedown or stabilization, and then we are going into resilient. But stress history becomes very important in permanent deformation, right? But to answer your question, no, there is no stress history considered. Okay, let's get started. Others will come, but we need to get started. So this is the stopping point where we decided, and the whole concept of this goes back to the first day when we talked about uh, resilient or elastic strain on top of the subgrade being the one of the critical response parameters that is going to predict your rutting. And I did mention something on the first day that all our pavement analysis programs that you see in practice, 99% in the research are all elastic programs. So what you get are elastic responses, right? So you're talking about elastic strain being predicted, computed on top of the subgrid, and you are using that to predict rutting, which is a completely plastic phenomenon, right? So this is a test result, and the x-axis is epsilon r, or resilient elastic, you can call anything, right? Because resilient response is essentially elastic response. So you have that, and epsilon p at n equal to 1000, so it's basically plastic strain for the same material at n equal to 1000, right? And if you see here, as the CBR of the material changes for the given resilient response strain or elastic strain, you can have multiple plastic strains. Does that make sense? You have, so the different lines are for different CBR, same material, and you are subjecting it to the same amount of elastic strain, let's just say 0 point whatever 22 or something, whatever it is percent. As you can see, it intersects all these 4 lines at different values of epsilon p, right? What that means is that as the strength of the soil changes, the same elastic strain can lead to different plastic strains, right? That is the reason you would rather have a CBR relationship to epsilon p rather than an epsilon r relationship to epsilon p. So this all boils down to the argument that don't just use elastic strain to predict rutting. Now I said CBR. What is CBR? A strength index. What is best correlated with strength index? Some kind of a stress, because stress is nothing but value of stress it can take, right? That is the reason behind the entire argument of why stress on top of subgrade is a better indicator of strain, permanent deformation, than strain on top of the subgrade. Granted, if you run a plastic analysis, then of course strain is the best, because strain directly is your permanent strain. But you are doing elastic strain, right? So that is the entire reason we actually vote for saying that rather use a strength and stress kind of a prediction approach rather than using an elastic strain. That's the reason when you track critical pavement response parameters, track the vertical stress on top of the subgrade, not vertical strain on top of the subgrade. Capture the stress, then compare that to your unconfined compressive strength, your shear strength, whatever. You have CBR, compute an unconfined compressive, do something, and then you can have a ratio and stuff. That's what your sub SSR is. So this is a very important thing. Let's also take a look at that. Limit epsilon r and epsilon p will be okay. That has been the understanding for a long time. Limit resilient strain or elastic strain, and permanent will be okay. But look at some of the different algorithms. There is Asphalt Institute, there is TRRL, which is in UK, there is Belgian research and stuff, and there is actually this is the model epsilon v vertical is L1 over n to the power m, very similar to a n to the power b, very similar. There's no, I mean, just model different, little bit of a different, but look at how different the model parameters can actually be. So you know you have similar values. The rut depth is 0.5 here, 0.4 here, 0.8 here, right? So similar kind of resilient strain measurements or thresholds are leading to different values and stuff, right? So it's not a very good approach. Look here, microstrains, allowable microstrain in the subgrade, AI and Shell, Asphalt Institute and Shell, n equal, this is the number of ESLs, number of load applications, basically runs up 5 million, 10 million and stuff. You have allowable strain is 799, Shell says 1575, 478, 885, 286, 498 and stuff. Because epsilon R or epsilon E, whatever you want to call it, elastic and plastic, it's not a unique relationship. It changes when your subgrade strength is changing, right? That's the reason track stress, that's a lot better because you can compare it with strength directly. That's essentially what the bottom line is. So for epsilon p is 2%, which is this graph, what are allowable sigma d and mr pairs? Okay, think again, I am allowing epsilon p is 2% permanent strain, plastic strain. What are my allowable mr and sigma d pairs? What it's saying is, if mr is 14,000 psi, your sigma d should be about 20. If mr is 75, your sigma d should be whatever, 100 divided by 6.89 or whatever that comes to be and stuff like that, right? So your epsilon p you can limit, then resilient modulus and sigma d, it has to shift based on the resilient modulus. Okay, again, why are you going down to? You're actually going to dynamic deviator stress, you're going to stress. That's how you're limiting your numbers. Okay, now comes the rutting model in MEPDG. Okay, this is the scariest looking model that you will see, at least in this short course, right? And it indeed is very scary, okay, because it has some models, some resilient strains that you get, some epsilon 0, which is a material property. There are some there is vertical strain that you actually calculate using the layered elastic analysis and stuff. It actually came out of, again, Professor Litton's group back in 1989, and a version of that was adopted into MEPDG. The major difference is in Professor Litton's model, his model parameters like epsilon naught b and sigma rho, they were only dependent on stress. But in MEPDG, there is other material properties that are included here as well to predict. Okay, the MEPDG model is quite complicated to understand, to implement and stuff. And also, if you go into the details, so there was a proposal we were working on back in 2014 or something, and I actually was I was the postdoc, so I actually was doing all the work. I actually went back to Professor Chuck Swartz, who is now retired. I mean, he retired from Maryland. He's now teaching in a university. He was actually the behind the entire unbound material part of MEPDG. He was back then in Maryland, and he used to work with. I mean, he was collaborating with Professor Matt Witzak. So Swartz was a part of the proposal as well. So he helped me understand how the heck this thing was developed and track it down. Bottom line is, once you go really into that appendix, I think it's GG or something, I don't remember anymore, it's been more than 10 years. When you go into that, you will see that you do all these calculations. At the end, there is an assumption there saying that just because we saw in Asho road test that 70% of the rutting was coming from the unbound layers and stuff. Anything that is happening, we are going to just throw a 70% number and we'll just call it good and stuff. So what I'm trying to say is there is a lot of complex mathematics happens, and then in the background there's a little bit of cheat happens to go. That's essentially the shift factor and stuff, right? So for all honesty, calibration of this based on your material for MEPDG implementation has pretty much been impossible and stuff. There is I'm not familiar with anybody who has actually done this entire calibration and stuff. So what I'm going to do here is I'm going to say a couple of these. Oh, by the way, this is aggregates again, an to the power b, and remember how we focused on SSR, subgrade stress ratio. Here we are focusing on sigma 1 over 3 because there is no QU in here, right? So we'll do that. But what I'm going to show you is another approach, which I think I shared that paper with you. If not, I think I did. I'll show you that. And we proposed a model about 10 years back, which does a much better job, at least in our view. Couple of things. An to the power b, what are the factors that are considered? I told you A is related to magnitude of permanent deformation at first cycle. That's what's written over there. You remember that. And B is the rate of permanent deformation. It's the strain rate. If you do a differentiation over there over n, you'll see that that's what B is basically, right? So that's what A and B values indicate. And there is another model. I don't know how to say his name. I have always said it Kedder, but I don't know if that's the right pronunciation. But they also propose something called a strain rate model. So they are predicting absolute strain per every cycle. They are predicting strain rate per every cycle. So d epsilon over dn, rate of accumulation, right? So obviously go down, right? Because when your curve becomes flat, your rate is going down. It starts at a very high value, it keeps going down. That's what this rate model is. Okay, in the show road test, again rutting, this is what I was trying to say, delta AC plus delta granular plus delta sub base, and you can actually calculate the strain rate and stuff like that. This is again for unbound granular materials, how the Seng and Litton model and how MEPDG model is. Okay, so this is what I wanted to go, checking the accuracy of the MEPDG model. This is a paper we wrote back in 2014, I think, or 15, I don't remember. Liang Chow was a master student. I was the postdoc at Tubler. So we actually developed a model. The name is actually CMT, Chow Mishra Tubler, and we actually proposed how to study the rutting in a better way, more representative way than what the MEPDG was doing and stuff. So let me show you what this was. Okay, 2014. So what we did is we took like a standard pavement section and we had test results for all the layers, shear strength and permanent deformation, resilient modulus, all materials we had tested, and we simulated an 1,000-pound wheel load with 80 psi tire pressure. 80 psi would be 550 something, probably 560 close kPa, right? And then MR varied with aggregate type, and we took a mu of 0.4. Subgrade layer we just simplified because we were trying to simulate MEPDG, so we said 55 CBRH plus 0.64. We didn't do stress dependent, right? And determine aggregate resilient modulus from repeated load permanent deformation. Like when we had a little bit of a stable behavior, we would take the resilient strain, we divide it, and then we take aggregate modulus, and then we analyze the same pavement using MEPDG. So we basically put in MEPDG to analyze what it is doing, and we actually knew how much it is performing in the lab, right? So the whole idea that we saw is material G1 was here, and then all the other three materials were over here at the top. They were kind of merged together. G1 was the low, then G2, B and L, they were all at the top. And if you look at it, G1 is 31,000 psi, and this is 21,000, 20,000, 20,000. So if you look at it, the MR values for the three materials are very similar. Rely on resilient strain to predict permanent deformation. Obviously, if your resilient modulus values are similar, it's going to predict a similar value. Right? That's what we saw. But then there is a different, we plotted against sigma d the 10,000 cycles, and then as you saw, this was here, material L was over here, material G2 was over here, material B was over here. So it's very, very different permanent deformation strain patterns. This is actual lab data. So we are like, why is this not being reflected in your MEPDG? If your material is so different, MEPDG is just because the resilient does not mean permanent deformation should be similar, because it's elastic versus plastic. So then this is the model we proposed. We said a n to the power b, and we are going to include sigma d in there, which is deviator stress, and then we said something called tau f over tau max, and this is what I was saying we're going to dive deep into in this session. What is tau f over tau max? Okay, I think the best way would be, no, I think I can do it here and the board. I don't need to switch. Look at the Morse circle. It looks scary, but it's not very scary. You draw the Morse circle, right? And then because you have the shear strength test, what did I say? Cutting is related to shear strength, not resilient modulus, right? Shear strength. If you have shear strength, you can calculate the failure in inclination, right? 45 plus phi over 2, right? So that's what this is, 90 plus phi, right? In Morse circle, everything gets doubled, remember? So 45 plus phi over 2 is basically 90 plus phi. So when you plot that, and then you calculate tau f and tau max. So let's try to decode this. What is tau f and what is tau max? Tau f is the shear stress on the failure plane, right? Tau max is the shear strength of that failure plane. Like when tau f is tau max, what has happened? Failure has happened, right? So do you see how it is similar to sigma d over qu? It's very similar concept. Instead of doing a normal stress sigma d over qu, I am saying I'm going to take the failure plane, measure its shear, and then I'll compare it to the coordinate of the Mohr Coulomb failure envelope. That's my shear stress ratio, SSR. Remember I said today SSR can mean two things, subgrade stress ratio or shear stress ratio. So this is what we did, is we said it's a shear stress ratio, and we actually incorporated that into the model. Okay, we said it's not just a function of the deviator stress, it is also a function of the strength, right? Just stress is 100 kg does not mean everybody will collapse. I will collapse, but a bodybuilder probably 100 is nothing for them, right? So that's the reason we incorporated this model into this parameter into that. We said we're going to consider not just stress state, but also we're going to consider strength in there, right? So then we modeled it, okay, and look at the actual performance and the predicted performance for different shear stress ratios. So in the repeated load triaxial testing, we knew the strength, we applied increased the deviator stress, targetly, so that we can target different tau f over tau max ratios and stuff. And we went all the way up to 0.75, which is bad, right? So you have 0.25 pretty flat, 0.34, 0.5, 0.75. It's getting progressively bad, right? So this was actually a pretty well received paper and a model that where we proposed, saying that no, we are going to not just rely on the MEP-DG model, which relates on resilient strain. We're actually focus on stress instead, stress and strength, and then just use the basics of Mohr circle. So this scary thing is nothing but the sigma f. You can do it. You can do it analytically. It's just trigonometry right there. Nothing special. Okay. So then we can look at some field permanent deformation results. This is in the NAPTF, that I said, National Airport Pavement Testing Facility, and flexible pavements 5 to 10 inches of AC, CBR 4 to 8, and foiled with up to 4-inch truss. Highest contribution is often in the base layer and stuff, which is P209. So at major contribution, at wheel loads of 45,000 to 50,000 pounds, which is typical for aircraft. Now we are talking about big aircrafts, right? This is airfield pavement, not highway pavement anymore. So you are now talking about major contribution to permanent strain actually coming from the P209, which is the base, versus when it increased significantly more, then your subgrade was contributing more. So what I'm trying to say is the depth, at what level you are failing, or how much is your rutting. Can you isolate your base versus grade? At some levels, base will be much higher. At some levels, subgrade will be much higher, right? So it can change. So factors affecting delta P, primary factors, sigma D, epsilon, sigma 3, and the ratio and strength and tau max. So we added those and saying that what is the maximum shear stress that is applied on the failure plane, and the tau over time max, and number of load cycles. Secondary factors, dry density. Now density is a very interesting thing that has helped us, escape or cheat for a long time, right? Because density is not a mechanistic input. None of your designs require density. Well, some analysis may require, because they want to calculate. So H is the only role that density plays, and surcharge is very small anyway. But the good news is that in a lot of ways, density kind of correlates with strength and stiffness, because better packing leads to better performance and stuff. The problem arises when you have something like railroad ballast or open graded aggregate, where density just cannot be established. It's just not possible. There is so much void, you cannot stick a nuclear gauge in it and do it. It's full of voids. That's when you run into challenges on how to do this. Percent crushed, uncrushed versus crushed stone. This is actually something Dr. Sahu was just mentioning over tea, that some of the material in bases here can be pretty flaky and stuff if there is no quality control and stuff like that. That can be very challenging, right? Because flaky material, what's the main problem with elongated material? They're going to break, right? So whatever you have done, whatever density you tested or measured, it has now changed because the material has changed, right? So your packing has changed, your orientation has changed, and now you can have really big problems. Fines content, as I said, fines and permanent deformation have a very interesting relationship. When fines are optimum and they are dry, the system behaves pretty stable, because the big rocks, the way I explain it in undergrad classes is, imagine this room full of basketballs. Okay, now throw in a few tennis balls in. Now throw in a few table tennis balls in there. right? That's a well graded system or something like different representation and stuff. What role do the tennis balls and the table tennis balls play? They stabilize the matrix, right? They fill the voids. The big balls are not moving widely and stuff with a little perturbation and stuff. The problem happens when there is water. A high fines material can just collapse with water because water plays the role of, or makes it like a slurry. Basically, it's a lubricant now. Now you have greased the contact points and stuff, and they're going to just slip past each other, right? So the fines is a very tricky concept, right? Where you start. Important if fines moisture content. This is very interesting. Moisture content is important if fines are greater than 12%. This is actually one of the findings of my dissertation, my PhD work is I separated different bins and we did them manually. 0% fines, 4% fines, 8% fines, 12% fines, 16% fines. What we saw is when you have less fines and you add water, water just drains. So your fines are not really hurting you as much. The problem is when the fines cannot escape and the water just wets them, now makes it a slurry. That's when the problem is. Now the system collapses, right? So it's very important to realize where it is. And then I think you just asked stress history effects. Stress history is very important for permanent deformation. How do I explain stress history? Let's just go back to our weightlifting thing. I have never lifted a single weight in my life, okay? Like for weightlifting, I may have done some exercises, but never have lifted weight. Now if I go and on day one lift 100 kgs, it's going to break my back, right? The way to start is 20 kgs, 40 kgs, 60 kgs, 80 kgs, 100 kgs. You build it up. Stress history is exactly the same. If you build up stress history slowly, then aggregates will actually resist quite good and stuff. If you go from the top to the bottom, it just falls apart, right? So it's the packing that is very important. I think we talked about this already, the tau f over tau max. Again, you're asking about the ratio, 0.6, a magic number. Keep that below that, and you'll be fine with rutting. And anybody doing, triaxial tests in your labs, you can try this out. You can just, set this formula, set it up, calculate, do a shear strength test. By the way, so many people doing resilient modulus tests. How many of you have actually done shear strength tests on aggregates? That's not good news. You need to run that, right? Shear strength, first thing, it's very difficult, I understand. Resilient modulus is easy to play with, right? Stresses and stuff. Shear strength is difficult. But the strength, actually, and when I launch ELIPAVE today, you will see why strength is important. You can actually cut off the stress distribution. Actually, it's beautiful how Professor Thompson imagined this. The way the software works is at any node, if the stress actually increases the strength, he actually collapses that and he redistributes, saying that this element does not exist anymore. It's not going to take any stress because the stress is more than the strength. So he actually redistributes the entire thing and stuff. It's beautifully imagined. I don't know how to do it mathematically. CCP tests, 9 psi, 15 psi, 21 psi, 27 psi. At confining pressure 3, you just, this is a sigma d over sigma 3 of 9, sigma d over sigma 3 of 3. As the deviator stress increases with number of load applications, the permanent strain increases. This is confining pressure effect. Okay, axial permanent strain. Let's just say 0.6. Let's fix a 0.6. When sigma 3 is 3, you are only taking 25 psi. When sigma 3 is 8, you are taking 45 psi. When sigma 3 is 10, you are never hitting this. That makes sense? What does that mean? The tighter you hold, you look confused. This is, pick an axial strain, let's just say 0.4. For sigma 3 equal to 3 psi, at 15 psi deviator, you are hitting 0.4. At 5 psi, you are hitting it at about 20. At 8 psi, you are hitting it at about 35. At 10 psi, this is kind of higher than that. I don't know how that works. But you never even get there or something. So what essentially is the tighter you hold the material, the greater stress it is able to take before it accumulates some permanent strain. That's the saran wrap example, right? The kitchen wrap, and with your marbles and stuff. This is sigma 1 over sigma 3. Again, tau f over tau max is a little bit of an advanced way of looking than sigma 1 over sigma 3. Similar stuff, right? We're not talking about shear or shear plane now, we're just talking about principal stress ratio, sigma 1 over sigma 3. Here, look, 30 over 15, 20 over 5, 30 over 5. This is sigma 1 over sigma 3 is equal to 7. Okay? This is sigma 1 over sigma 3 is equal to 5. No, 4. Sigma d over sigma 3 is 4, but sigma 1 is 5. The ratio, right? So what this is essentially saying is you have very, very high confining stresses here with respect to this, and then the ratios, as you keep changing, they're also sometimes how much confining, how much stress you are able to withstand and stuff, it can change based on the material and stuff. This is sigma 3 is 10 psi. This is actually Dick Barksdale. This is my advisor's advisor, my academic grandfather, 1972. You know, my academic grandfather's grandfather or somebody like that is actually Terzaghi. I actually have a lineage, academic lineage tracked over it. So soil, you know Terzaghi, right? The father of soil mechanics. So yeah, I come from royalty. So this is Barksdale's work. This is n is increasing, and as you have sigma 3 is equal to 10, this is sigma d over sigma 3 4.6. As you keep increasing, your epsilon p increases. Very similar to tau over tau max. Very similar, but on different terms. Stress dependent Roding models. What are the different Roding models available? You know, there can be again just a sigma 3 to the power b n to the power c. This is where you are only including the confining stress, right? This is only the deviator stress. This is now the deviator stress ratio. This is now deviator stress, and this separately. This looks very similar to that you know, a version of the Uzan or the Pezos model, basically the UT Austin model and stuff, where they have actually sigma d and sigma 3 separately and whatnot. And then you can actually do Rutting model parameter A as a function of deviator stress. Remember, one of the major criticisms of the phenomenological model is that it does not take into account stress. But the defenders of that, or who believe in simplification, they actually say, look, if I apply deviator stress and plot A, I get a 0.97 correlation. So A is actually directly affected by stress. So even if you don't have it in the formula, it is indirectly in there, right? It's not the end of the world. This is actually some shakedown work, people who work on shakedown. This is very, very relevant, folks. Why? It's because the load level does not necessarily stay the same all the time. It can increase. One example is actually in the railroads. right? In the railroads over the years, they have actually increased the axle loads and stuff like that, right? And as you know, tracks don't get reconstructed very often. I mean, tracks are very long standing and stuff. So what you can do is you actually stay there, and then you can, now your sigma d is all of a sudden greater, and you see significant difference. This is the collapse phenomenon. Look, this is 63 kPa 0.5, and now this is 336 kPa. It increased significantly, but look, it actually goes over here, and then when you increased it, now the gap between the two is also significantly greater, right? That's basically saying that, just because under one stress state it was behaving similarly, when it changes, it may not. What does this mean? It means that if I'm running a 100-meter race with somebody, maybe I'm close to that person, but the moment it becomes a 800-meter, I probably never finish, right? So this is stress, that's stress dependency, right? Just because you see something, that's the danger of extrapolation. You run this test and you're like, oh, the materials are different, go use it and stuff, and then like, what just happened, right? Because that's stress dependent material. You don't extrapolate. This is related to, I think, again, you were asking a question about the morphology of the material and stuff like that, right? What ranges? No, but here level has changed. This is not repetition. What he's referring to is this lady called Sabine Werkmeister. She's she was from Germany, and she did some pioneering work on shakedown theory of aggregates and stuff. And that's what he's referring to about her ranges. She says like range A, range B, and range C of behavior and stuff. But I think what you are confusing is, your statement would be true only if the variable here would have been n. Look, here the sigma has changed as well, right? You are talking about just based on n if it is changing, and that happens too. That happens too. It's all, remember I said, not fatigue can be picked up as fatigue related. Like even if it is not, load law is not changing, just repetition can sometimes collapse your material. You can just go. That's one aspect. You're talking about phenomenological as well, like slag and all of that when you march. Right now you're talking about angularity changes, surface texture changes, packing changes, right? This is, whoa, okay. So this is actually something called the University of Illinois Aggregate Image Analyzer that, my advisor had built. He has now built something called an EUI-AI, enhanced in University of Illinois. But anyway, the bottom line is it is a set of cameras, 1, 2, 3, 3 different views, takes pictures. It's actually a treadmill. This is a treadmill. It runs very slowly, aggregates pass on it, and the cameras keep capturing, and the lab view code just goes and calculates the AI. It's image thing. These days you can do it in 15 days probably. What these people did as their dissertation, because these days it's becoming very easy, image analysis. It's actually, one of my students, I was so proud of her, a master's student. She was doing some discrete element modeling, which happens to be another one of my mentors. We're not going to go into that. I told her, I said, I want you to capture this unbound aggregate shape and import it into DEM. She's so resourceful. She went to Autodesk and found a version of a student software. I don't remember the name. Autodesk is the company that makes AutoCAD. Desk found some kind of a free version for students, used our cell phone and like just as Android, just took pictures from all around and then imported into that software, and within 4 hours she had that image for me completely digitized and quantified and stuff. Like, here is your image. Talking about a master student, I mean, I was blown away. So what I'm saying is these things can be done very easily for you now. I mean, you can do it. You can just capture images, use some ready-made Python algorithms to detect edges and stuff and quantify what is known as angularity. Bottom line is, as angularity index increases, friction angle increases significantly because it's an interlocking, right? And if friction angle increases, what are you increasing? Your tau f, sorry, your tau max is increasing. So for the same stress state, tau f over tau max is now very, very low. So now you are completely stable, right? So hence the importance of quality control. Hence the importance of at least this many crushed edges and stuff like that. It's not just garbage, you know, it increases strength significantly. You need to remember that. Right? Effect of density, okay, depends on what kind of material you have, okay. If you have 90 PCF, 96 PCF, 99 PCF, number 4, it's a number 4 stands for ASTM number 4 gradation. You can look up ASTM number 4. Oh no, sorry, this is my bad. This is ARIMA number 4. It's not ASTM. This is railroad. So it's relatively open graded material. If you density, if you pack it better, your permanent deformation becomes very good. Hence the importance of compaction, right? Again, remember I said railroads and pavements are very similar. I don't know how many of you have seen railroad construction track. Do you know what a track stabilizer is? Has anybody heard of it? Okay, so you know what a roller is, right? A compact, like a steel drum roller. You've seen that very, very common, very often. A steel drum roller is something that you use on pavements all the time. On railroads, there is nothing called a steel drum roller. You're building a track, and ballast is actually not really compacted. So what they use is something called a DTS, dynamic track stabilizer. It's a train. Remember, I don't know if you know this, but railroad tracks are constructed using trains. Trains actually construct themselves. So basically, all the track vehicles are trains. They're not like coming from the side or anything. They lay something, they go, they lift themselves up, they put it in. It's fancy. It is cooler than heck, if you want to see. So DTS is a train, basically like a vibratory compactor kind of a train that actually vibrates the track and stabilizes it, right? And if you do that, and it's very difficult to do, and especially people get scared when you are near a bridge or something, because you can have resonance and the bridge can collapse and stuff if you're not very careful and whatnot. Yes, can work up to a certain point, and then at the bridge location they kind of get off. They're like, oh, I'm not going to vibrate this anymore and stuff, and that is where all the problems start, right? So it's compaction, very, very, very important. Fines. This is very interesting. Like fines, yes, increase number of percent of fines, it increases, epsilon p increases, but as I said, the effect is lot more. This is my work. This is 27.1. This is what I was talking about. 16% non-plastic, 12% non-plastic, 4% non-plastic, 8% non-plastic. So above 12%, because it is optimum moisture content, it's not dry. It's like there is enough water. So when you go above 12%, the permanent deformation starts increasing significantly, right? This is what I was referring to. This is another one. This is, look, plastic fines. This is plastic, 90% wet of optimum. It's on the dry side, but plastic on the dry is actually worse than non-plastic on the wet. A lot of times plastic fines are very, very slippery, very sticky and stuff. So this is all, constituted samples, manually blended and stuff. Look here, G is gravel, and this gravel is uncrushed material. Okay, what is special about uncrushed material? They are kind of spherical, right? If it is spherical, what is the void space? More or less than crushed materials? How much? What is the most efficient packing you can have among particles? What shape? So I'm talking material science now. I'm not talking civil engineering. Well, you never have cubes sitting on each other, right? Is it angular or is it spherical? Where is your, what minimizes your volume, voids? Spheres. Spheres minimize your void. So uncrushed material actually has less void than a crushed angular material. Okay? So when you have 12% fines in less, it actually more full than 12% fines in a greater voids, right? So the gravel at 12% actually collapsed, whereas the limestone and dolomite were crushed at 12% did not collapse. It's about how full you are. It's all about voids. It's all about void structure, right? That's very, important. Stress history effects. Okay, low sigma to high sigma, epsilon P is very low. I told you this already. Gradually lift weights, your collapse is going to be much lower. High sigma to low sigma, epsilon P is very high. If you start with a very big one and then you reduce and stuff. Okay. Now do you realize why in the resilient modulus test in the aggregates it's actually increasing orders? Right? You're actually trying to systematically apply more and more load. This is stress history effects again, loaded at 20 and 1 confining and 336 axial. So specimen conditioned at, this specimen is conditioned at 21 kPa confining and 336 axial deviator stress right here. And this specimen is 21 kPa confining and 105, and this is unconditioned specimen. Okay, so when you don't condition it, apply everything same load, it's going to, you have to condition. That's the stress history effect and stuff. This is, if a model does not consider the effect of stress history, the trend is quite different from the measured one. If you don't measure, like, this is important, folks. What stage are you trying to model? Are you only trying to model this portion without considering how it went? Right? So if you're trying to develop a proper model for all different stress states and stuff, you have to consider different stress stages and stuff. Design concepts, rutting due to base compaction and rutting due to shear in base. This is two different things, compaction versus internal shear. Compaction is good, you're just compacting, just means that you didn't compact very well, right? Shear is different. Now your tau over tau max is a problem, right? So tau max increases, epsilon P decreases, tau over tau max increases, epsilon P increases. I told you this already. Right? When your angular material, your strength increases, so your tau max is increasing, so your permanent deformation is very low because you're at a lower level, you're playing at a lower percentage and stuff like that. This is shakedown stuff with the whole idea of how shakedown happens. There is first step, it's called plastic shakedown. Then slowly it increases to what is known as plastic creep, and then there is a stiffening response, and then what is known as incremental collapse. So just the same load, unless it is very, very low, if you just keep applying and applying and applying and applying, at one point it's going to fail. Okay. Now we're not going to go into deep into this. This is the ABC stuff I told you. This is the Sabine Werkmeister I referred to. This is her dissertation work. Need for advanced research on delta P. You have some data, but then beyond that, future large generation aircrafts and stuff like that, you don't know what the load is going to be, right? Why do you need that? Your pavements, you're going to use recycled materials, you're going to use other kind of materials. You have to study mechanistic methods to do this. Okay, this is some shear concepts. I'm trying to switch. We talked about principal stress rotation. I want to show some stuff related to railroads. Okay, I'm going to switch now to a rail